Okay, so we're here. It's Wednesday, August 26, 2020. We're here today to talk about subatomic particles and isotopes. Okay, so we have this little table here. We know there's three different types of particles inside atoms: neutrons, protons, and electrons. Okay, so we're going to discuss various aspects of these. First is location, where they are in an atom. So protons and neutrons, as we should know, are located, why is that not writing, in the nucleus of the atom, in the center. Right? And the protons are also located there. Right? And the electrons orbit the nucleus. Now, I don't know, because of these COVID circumstances, if we're going to have time to later in the course to talk about the Rutherford scattering experiment, but I just want to try to emphasize to you how small the nucleus is compared to an atom. An atom is on the order of, and it's worth knowing this, an atom has a radius on the order of 10 to the minus 10 meters. Right, 10 to the minus 10 meters is a typical atom. The radius of a typical atom. Radius of a typical nucleus is on the order of 10 to the minus 15 meters. All right, so we see the nucleus is way, way smaller than an atom, but it's even worse than that. This is 5 powers of 10 difference, 100,000. So the radius of an atom is 100,000 times bigger than the radius of a nucleus. All right, 100,000 times. But atoms are not one-dimensional. They're three-dimensional. So what sort of shape does an atom have? It has the shape of a sphere. Atoms are some of the most perfect spheres that we know of in nature. So the formula for the volume of a sphere, it's more appropriate to compare the volume of an atom to the volume of a nucleus rather than their radii. And when we do that, the formula for the volume of a sphere is 4/3 pi r cubed. So this radius here, these radii need to be cubed. They need to be cubed. So when we do that, we see that an atom is 15 powers of 10 larger than a nucleus. 15 powers of 10 larger than a nucleus. 15 powers of 10 is 1,000 trillion. 1,000 trillion nuclei can fit in one atom, right? I don't know about you, but I'm rather amazed by that. 1,000 trillion nuclei can fit in one atom, okay? And it's good. We're going to see even some more amazing things with respect to that in a few minutes here. So I'm going to erase these two numbers here. Do we have any questions about that? Okay, 1,000 trillion nuclei can fit in one atom. Okay, let's see. Okay, so what's the electrical charges on these? Well, a neutron is where it got its name from. It's zero. It's neutral. Remember, neutral means doesn't take sides. It's neither positive or negative. A proton has a electrical charge, a relative electrical charge of +1, P proton, P positive. Electron has a relative electrical charge of -1. So the size of the proton and electron charges are equal to each other. It's just that one is positive and one is negative. One is positive and one is negative. Now, just to pique your curiosity here a little bit, what do two positive charges do to each other? Do they attract, repel, or do nothing? Two positive charges. Attract, repel, or do nothing?
Well, if you have multiple positives, they would repel each other.
They would repel each other, most definitely. What would two negative charges do to each other?
Repel each other.
They would repel each other again. In other words, like charges repel. What would a positive and a negative charge do to each other?
Attract each other.
They would attract each other. That's what holds an atom together. The electrons are orbiting the nucleus. So those negative electrons orbiting the nucleus are attracted to the protons. That's what holds an atom together. Now I pose this question to you guys. We said here that all of the protons are in the nucleus. And whoever was answering there said that positive charges repel each other. Now the nucleus is extremely small. Again, we said 1,000 trillion nuclei can fit in one atom. So how is it in the nucleus the protons are practically touching each other along with the neutrons? And protons repel each other explosively. How is it that a nucleus stays together? How is it that a nucleus stays together? Anybody want to hazard a guess at that? Because we know positive charges want to get as far away from each other as they can. And yet in a tiny nucleus, we have positive charges sitting right next to each other, and it's stable. Okay, it's stable. The nucleus does not explode. But according to what we just went over, no nucleus should ever exist. Or in other words, the only nucleus that should exist is hydrogen with just one proton. As soon as we go to helium with two protons, those two protons want to get as far away from each other as possible. Yet, we know a helium atom exists, a helium nucleus exists. We look at a uranium atom, it's got 92 protons in it. All of them want to get as far away from each other as possible. How is it that uranium nucleus, that matter, any nucleus, how is it that
That's due to the strong nuclear force.
Very good, very good. Who said that?
That's Joseph.
Joseph. Very good, Joseph. That tells us there must be another force inside the nucleus, and it's the strong nuclear force. It is about 100 times stronger than electrical forces. So the protons are being repelled, but there's a force 100 times, the strong nuclear force is 100 times stronger than that repulsive electrical force, and that strong nuclear force is pulling them together, holding them together. Okay, so very good, Joe. The only thing here is the strong nuclear force only operates over extremely short distances, roughly the width of a proton or a neutron. Once you get further away than that, the strong nuclear force, the strength of it drops to about approximately zero, right? Zero. So even in the nucleus, suppose you have a calcium nucleus with 20 protons, a proton on one side and a proton on the other side of the nucleus, they are exclusively being repelled by the electrical force. They are too far away to be attracted by the strong nuclear force. They are too far away. Okay? All right, but that's not really what we're here to talk about today. Now, let's take a look at absolute masses. All right, and we'll write these up here. Okay, and I'm going to write up here the absolute mass in kilograms. Okay, hopefully you can see that. 1.6749 times 10 to the negative 28 kilograms. Okay, and for a proton, very similar. All right, 1.6726 times 10 to the negative 28 kilograms. Okay, can you folks actually read these numbers without me saying?
Yes.
Okay, and electron is a lot less massive, a lot less massive. 9.109 times 10 to the negative 30, 10 to the negative 31st kilogram. 9.109 times 10 to the negative 31st kilogram. So we see here that the masses of protons and neutrons are almost exactly the same, right? And then the electron is 3 powers of 10 smaller, 3 powers of 10 smaller, okay? Remember, 3 powers of 10 is 1,000, right? So it's on the order of 1,000 times smaller, right? Now, I don't know about you, but my simple mind cannot comprehend numbers 10 to the negative 28 or 10 to the negative 31. I mean, most human beings, our minds just cannot comprehend because we're not used to in everyday life to dealing with numbers that small, right? Our minds, I mean, we have no problem dealing with 100 or 1,000, maybe 10,000, maybe even 100,000. Once you get beyond like 1 million, it's kind of tough to comprehend. And remember, a million is 10 to the 6th. These are 10 to the 20, negative 28, 10 to the negative 31st. These are really, really small numbers. So what we do is we form a relative scale here, a relative scale. And I'm going to write those up here. And then we'll talk about what we mean by a relative scale here. So this is 1839. This is 1836. And this is 1. Okay? So let's look at an example. We'll come back to this. We'll just do this with an analogy, and I think it'll re-emphasize the point here. Suppose we have a family, a dad, a mom, and a baby, right? And let's say that the dad has a weight of, let's say, 240 pounds, a big guy. And the mom is a little petite. She has a weight of, let's say, 110 pounds. And the baby has a weight of 10 pounds. All right, so those are, here, let's write the units on there. Pounds. We shouldn't be using pounds in science class, but I think that's what most of us are familiar with. All right, so these are absolute weights. How do I know they're absolute weights? Because they have a unit attached to them. They have a unit attached to them. Just like up here, I know these are absolute masses because the unit is kilograms. Right? So these numbers are in kilograms, those masses. Right? But suppose I wanted to make a set of relative weights here for this family, for the 3 members of this family. So how would I go about doing that? I'm going to take the weight of the smallest person, the baby, and that's going to be my reference point. So I'm going to take the weight of each of the 3 members of the family and divide it by the weight of the smallest person, who is the baby. So 10 pounds divided by 10 pounds is 1. 110 pounds divided by 10 pounds is 11. And 240 pounds divided by 10 pounds is 24. These are the relative weights for the 3 members of this family. Notice there's no unit, because when I did 110 pounds divided by 10 pounds, the pounds divided by pounds cancels out. It's equal to 1. So there's no units on the relative weights, right? No units on the relative weights. Any questions there? Any questions? Now let's go back to our particle table. Okay, so where did these numbers come from? Well, the electron with the smallest mass is like the baby, right? And in this case, the mom and the dad have almost the exact same mass, almost the exact same mass. Dad is a little bit heavier. You notice here, this is 6749, and the proton is 6726. They're almost exactly the same, but not quite. Neutron is a little bit more massive. Okay, so where did these numbers come? This is the baby. So I took the mass of the electron, divided it by the mass of the electron. So of course I'm going to get 1. Here, for the relative mass of the proton, I took this absolute mass of the proton, divided it by the absolute mass of the electron. I get that number. And same with the relative mass for the neutron. I take the absolute mass of the neutron divided by the absolute mass of the electron, and I get this absolute mass. Okay, now this makes a little more sense. Okay, I mean, now we're at numbers that human minds can comprehend. Hey, I have no problem imagining 1,839. I have no problem doing that and comparing it to a mass of 1. I have no problem whatsoever doing it. So this gives us a good feel for how many times more massive protons and neutrons are compared to an electron. Can't really get that by looking at this here, because these numbers are so dang small. Okay, any questions there? Any questions or comments? All right, I'm going to erase our family down here. All right. Now, I have a second relative mass column up here. All right, a second relative mass column. And this is the one we're going to use mostly. But you should be aware that protons and neutrons are roughly 2,000 times more massive than the mass of an electron, right? So only this relative mass column is going to give us that. This last small mass relative mass column will not reflect that, okay? Now, suppose you wanted to weigh an elephant, all right? Weigh an elephant. Would you care if there was a fly on that elephant's back? Would that affect your result? Come on, somebody say something.
Yes.
It would? You're going to weigh an elephant and there's a fly on its back. Is that going to change? Is that going to change the scale at all? Are you going to care? No. Even if you weighed yourself, right? I weigh myself every morning, right? If there's a fly on my shoulder, it's not going to change the reading on the scale, right? It's not going to change that reading. Well, take a look at this. Remember, 2,000 pounds in 1 ton. So this is like 1 pound. These are almost 1 ton. Almost 1 ton. So these two here are like elephants, and this is like a fly. Right? Again, these are 1,800 times more massive than electrons are. So if I'm weighing an atom, I don't really care about the electron, right? Because they're so insignificant compared to the protons and the neutrons. They are so insignificant, 1,800 times less, right? So I don't really care about those, the protons and, or sorry, the electrons. I really, to a first approximation, if I just only take into account the masses of the protons and the neutrons, I'm good, right? And for most purposes, you're going to be okay. And you can ignore the minuscule masses of the electrons, which are almost 2,000 times less massive. I mean, you know, if you go buy a ton of, what do you buy a ton of? Say rock, gravel. You're going to put gravel in your driveway, right? And you go buy a ton, 2,000 pounds, right? If they only give you 1,999 pounds, I mean, are you going to cause a beef about that, right? Or if they give you 2,001 pounds, right? It's no big deal. No big deal. Who cares, right? All right. So what numbers are we going to put in? We're going to ignore the masses, the relative mass of the electrons. So we're going to call that 0. We're going to ignore it. We're not going to include it when we weigh this atom, right? Or I keep saying weight, but we're talking about mass, okay? Now, if we take a look here, the relative masses of the proton and neutron are almost exactly the same. Neutron is a little bit heavier, okay? So I'm just going to say, well, let's just set both of those equal to 1. Let's just set both of those equal to 1, okay? So this is very simple, very simple. If I have an atom sitting on the table, oh, and I want to know its mass, all I got to do is count how many neutrons there are, how many protons there are, add those two numbers together, I have the mass of the atom. I'll say that one more time. All right, if I have an atom sitting on the table, all right, I walk in, I want to know its mass. I don't even have to put it on a scale and weigh it, on a balance and weigh it. I'm ignoring the electrons. I'm ignoring the electrons. So I look at that atom, I see however many electrons, just ignore them, right? But then I count the protons. Each proton has a mass of 1. Each neutron has a mass of 1. Add those two masses together, I have the mass of the atom, to a very good approximation, right? Now, because I only see you guys like 27 or 28 days, I never have my college students do this assignment, but my high school students who I see much longer, I have them do this assignment. They reproduce they see how close they can get to the masses that are on the periodic table. Remember, we said those are relative masses, or sorry, not relative, those are average masses on the periodic table. The average mass of all the, so for carbon, for example, 12.011, that is the average mass of all the carbon atoms in the universe, okay? And because we're going to talk about isotopes here in a moment. Let's see here. So very simple, very simple. Just count the protons, neutrons, add them together. Okay, any questions here? All right, you should have a good idea of this table. You don't need to know the absolute masses. I won't ask you that. The only reason I put them up here is because they led us to this set of relative masses. This set of relative masses led us to this set of relative masses. Okay? Any questions or comments? Any questions or comments? Joseph, very good knowing about the strong nuclear force holding the nucleus together. You know, I want to mention, since I'm standing here in Los Alamos, just probably half a mile away, less than half a mile away, is the home of the guy. Oh my God! Every year I can never remember his name. That discovered the nucleus, and during the Manhattan Project, he was a famous scientist, so he had a nice fancy house, and it's over there. What's his name? Every semester this drives me crazy. I can never remember his name. It'll come to me.
Rutherford?
Say again.
Is it Rutherford?
No, not Rutherford. Rutherford discovered the nucleus, and somewhat gets credit for protons. J.J. Thomson discovered electrons. This guy, what's his name? It just bugs me. Because his house, there's actually a family that lives in his house. So there's a place called Bathtub Row. There's just like 6 or 7 houses on that street. And it's called Bathtub Row because during the Manhattan Project, they were the only houses in Los Alamos that actually had a bathtub. Those homes were reserved for the very, very famous scientists. But anyway, that's his house over there. It's over there by Fuller Lodge, if you're familiar with Los Alamos at all. Okay, any other questions up here? Any other questions? All right, I'm going to erase this. And if you have a periodic table, please get it out. Please get it out. Okay, and I'm going to ask you, I'm going to write some atoms up here on the table, and I'm going to ask you to point to those atoms on your periodic table. Okay, so let's look at, why does this brown one not work, and why do I keep it up here? Right, so we notice a neutral atom because the protons and electrons equal each other. Point to that on your periodic table. Point to that on your periodic table. All right, everybody have it. Everybody have it. Okay? All right, leave your finger there. Don't move it. Point to that atom on your periodic table. Okay? And leave it there. Leave it there. Don't move it yet. And one more. Okay? So now we're pointing to that last atom, 8 protons, 12 neutrons, 10 electrons. So what did you notice about your finger? Come on, somebody answer.
It didn't move.
It didn't move. So these atoms are all at the same location on the periodic table. They're all at the same location on the periodic table. All right? So what are these atoms called with respect to each other? They are called isotopes. Isotopes. Okay, it comes from Greek. All right? Now, here I'm going to split this word into 2 parts, a prefix and a root. What does this prefix iso mean? Anybody?
Alone?
Alone. No. You know, that's every semester, that's what somebody says, because they usually think of like isolated. Well, believe it or not, I kind of just gave it to you. It means same. It means same. Is anybody hiking here? No hikers?
I go on a couple.
Couple. And when you go hiking, what kind of map do you bring with you if you bring a map? What
Oh,
kind of
normally I
map?
just walk it out.
Well, if you were going to go on a new place you've never been, what kind of map would you bring with you? Here, I have a bunch of them right here. What kind of map is that? I don't know if you can see it. That's
I can
called
see
what?
them.
What kind of map is that called? A topographic map, topo map. And the topographic map gives you your location. So top means location. Location. So now we can see why these atoms are said to be isotopes of each other. They are at the same location on the periodic table. Same location on the periodic table. Right? So this is where this name comes from, isotopes. Okay? Any questions there? Any questions there? All right, so let's take a look here. We see if they're going to be at the same location on the periodic table, they better have the same number of protons, right? Atomic number has to be the same, which is equal to the number of protons. So isotopes have the same number of protons, but different numbers of neutrons. Different numbers of neutrons. Same protons, but different neutrons. Same protons, but different neutrons. Notice we could ignore the electrons. We could ignore the electrons. All right, the electrons don't matter. All right, that'll be next thing we're going to do. All right, does everybody understand that? Isotope, same location on the periodic table means same element, same atomic number. So that means same number of protons, but they have different numbers of neutrons. All right, now, let's ask this question. Take a look at that particle table that I just had up here a few moments ago. And we said that a very simple approach to looking at the mass of an atom was just to count the number of protons, count the number of neutrons, add those two together, right? That gives us the mass of an atom. So let's take a look here. I can write for the mass of an atom, the mass equals protons plus neutrons. Protons plus neutrons. Right? That's the mass of an atom. So this atom right here has a mass of 16. A mass of 16. This atom here has a mass of 18. This atom here has a mass of 20. They're all oxygen atoms. How do I know that? Because the number of protons gives me the element. Right? They're all oxygen atoms, but they have different masses. 16, 18, 20. Because the mass is equal to protons plus neutrons. In other words, when I write this equation, I'm using that last column on the particle table, the second relative mass column, where protons have a mass of 1 and neutrons have a mass of 1. And electrons have, oops, sorry, everybody see that? Okay, and electrons have a relative mass of 0. We're using that last mass column, all right? Any questions? You got a question, you need to speak up. Right? So it's very easy. We now know what isotopes are. Same element, but different number of neutrons. Same number of protons, different numbers of neutrons. Okay? Any questions before I erase this? Any questions? And we know what isotope means in Greek. Same location. Same location. Okay? I mean, think about it. I think I said this 1 or 2 classes ago. Be a scientist 100, 200 years ago, it wasn't just enough to know science. You had to know Latin and Greek also, right? So, any questions? All right, now, we have to have some way, some symbolic way of differentiating between these three atoms. Isotopes aren't concerned with electrons, so I'm going to erase the electrons. I'm going to erase those. Okay? One thing I do want to mention here is isotopes, as far as chemical reactions are concerned, they have essentially zero impact on chemical reactions, because chemical reactions deal with the valence electrons on the outer edge of the atom. All right? The neutrons are tucked away in that tiny, tiny, tiny nucleus in the center of the atom. So the number of neutrons does not affect chemical reactions whatsoever. Right? Isotopes are extremely important, and if we have some time, we'll talk about this a little bit. I might have to wait till next class, though. They're really important in medicine. All right. So how can we symbolically write the masses of these? Well, chemists use two different ways to do that. Two different ways to do that. One, we can just say oxygen dash whatever the mass is. And the mass is 16, 8 plus 8. This one would be oxygen 18. All right, and finally, the last one in green oxygen 20. 8 plus 12 is 20, protons plus neutrons. Okay? Actually, I just want to do one thing here. I noticed when I looked at the first, one of the YouTube videos, either the first or the second one, the image was kind of blurry. Nobody said anything. I can't tell that standing here until I actually look at the video. So they're all oxygen atoms, but they have different masses. All right, different masses. There's another way to write. These are called isotope symbols, or perhaps more properly, nuclide symbols. Nuclide. A physicist would call these nuclide symbols. Nuclide. And because they deal with the nucleus. Protons and neutrons are in the nucleus. These are symbols to represent the nucleus. Right? Now, let's take a look at that. The other way to do this. So you write the element symbol, and down here you put the number of protons, which is the atomic number. And up here you put the mass. Right? Up there you put the mass. All right? Now, this one would be oxygen again. Again, with the number of protons, which is the atomic number, and up here is the mass, which is 18. All right, and finally, you can probably figure this one out. O for oxygen, 8 protons, and a mass of 20. A mass of 20. Okay? So we have two different ways of doing that. Now, if I give you either way, I'm going to use the red one as an example. If I give you either way, you should be able to give me the number of protons and neutrons. All right? So let's look at this top one. If I ask you for the number of protons, well, you look for oxygen on the periodic table. Oxygen's atomic number is 8, so I know this has 8 protons. All right? Here's the mass, which I know is protons plus neutrons. But I know, because this is oxygen, of this 18, I know 8 of that 18 is from the protons. Right? This is just, remember, the mass is protons plus neutrons. Because it's oxygen, I know there's 8 protons. Right? So this tells me there's 10 neutrons there. 10 neutrons. Okay? Let's look at this one. Oxygen 20. All right, again, it's oxygen, so I know there's 8 protons. This 20 is protons plus neutrons. So out of the 20, I know 8 of them are protons. So the other 12 must be neutrons. The other 12 must be neutrons. Right? We see how we figure that out. We good there? Thumbs up or thumbs down? If you, most people have their cameras turned on. Remember, if you have your camera turned on, you're going to be on YouTube. All right, now let's look at the bottom one, the bottom nuclide symbols. Okay, again, this is, we don't need to look at a periodic table. All right, we don't need to look at a periodic table because here I'm given the number of protons. Up here, I looked at oxygen on a periodic table to get the atomic number, which is the same as number of protons, but that's given to me here. So I don't need a periodic table for this, right? I know there's 8 protons, and this is protons plus neutrons. Well, if there's 8 protons, and this is protons plus neutrons, there better be 10 neutrons. Okay, let's look at this one. 8 protons, and protons plus neutrons is 16. So out of this 16, I know 8 of them are protons. I know 8 of them are protons. So there must be 8 neutrons. There must be 8 neutrons. Okay? And, I'm going to erase this and put a few more up here. This is pretty simple. Once you do a few, it should be no problem for you to do this. It should be no problem. Once you do a couple of them. Okay? But we should be able to go the other way also. If I give you this on top, you should be able to give me what's on the bottom. Or, you know, these 2 things on the bottom, 2 different ways to write the isotopes. Or if I give you this or this, you should be able to give me this. You should be able to give me this, right? So it goes both ways. Any questions before I erase this? Any questions? All right, so we'll just do a few more examples. And I'm going to call on you folks. And please participate. Don't sit there like a bump on the log. All right, we don't need all this dead time on YouTube. So let's look at how many protons are in that?
43.
43.
43 protons. Very good. And how many neutrons? Actually, I meant to write 99, but that's okay. We'll go with 93. How many neutrons?
It's 50.
50 neutrons. 50 neutrons. You know, I want to say something. Like I said, I actually meant to write 99 here. So let's put 99. And why did I pick this isotope? This is far and away the most widely used isotope in medicine. I forget how many tens of millions. I have it somewhere on my computer. How many tens of millions of procedures every year are done using this isotope. And the incredible thing about it is there is almost none of it that occurs in nature. So this isotope has to be made by chemists, right? It has to be made by chemists. But it's used in tens of millions of procedures every year. All right, let's look at all right, how many protons?
11.
1?
11.
11. Atomic number 11. Now, how many neutrons?
13.
13. You don't understand where these numbers are coming from, you need to speak up. I'm not going to be at your home to help you or any of your classmates. Okay? So let's look at another one. Number of protons is?
92.
92. And number of neutrons?
46.
146. 146.
46, sorry.
All right. So 92 protons, and this is protons plus neutrons, so 146 neutrons. Okay. One more. Let's see here. You know, I have a periodic table right here. All right, let's do. How many protons?
26.
26. And neutrons?
23.
How many?
Or 33.
33 neutrons. All right, are we good this way? Or do I need to do a few more? Are we good?
Wait, I had a
Sure, go ahead.
question.
Yeah,
I don't get how the sun, how there's 26 protons on the sun.
I'm sorry, speak again?
Is that 26 protons?
Yes, 26. Because iron's atomic number on the periodic table is 26.
Okay.
So I look for iron on the periodic table in D block. And remember, the atomic number is equal to the number of protons. All right, it's equal to the number of protons. Maybe we better do one or two. Maybe we better do one or two more of these.
Yeah.
By the way, I remembered the name of the guy that discovered the neutron, James Chadwick. James Chadwick. So the house over there by Fuller Lodge, it's right next to Fuller Lodge near the library. It's kind of like a log cabin, but there's actually a family that lives in it. They used to have it was on the walking tour. There's a Los Alamos walking tour that relates to the Manhattan Project.
Discovered what?
Sorry?
I didn't hear what you said. He discovered what?
Neutrons. He discovered the neutron in like 1932 or so, 1933. You don't need to know his name though. You don't need to know his name. But I guess the family, they used to have a plaque out in front that said this is Chadwick House. But I guess the family that lives there must have got tired of people gawking at their house, you know, from right outside. And so they took away the plaque. It's no longer on the walking tour. All right, let's do one or two more of these. Let's see. What's a famous isotope? How many protons? It's in P block.
82.
80, how many?
82.
82. And how many neutrons?
126.
126 is correct. Okay. All right. Now let's do one more the other way. So again, these are called nuclide symbols. Nuclide symbols. How many protons?
17.
17. And how many neutrons?
16.
How many?
16.
No, that's 37.
Oh,
20.
20.
20?
20. 37 minus 17 is 20. All right, now let's go the other way. where I give you the protons and neutrons, and we have to write the nuclide symbols both ways. Okay? Because that's what you're going to have to do on your assignment. Again, these are very important in medicine. Very important. Odds are that almost all of us, at some point in our life, are going to have some procedure done, or either diagnostic or therapeutic procedure done using some radioactive isotope. Okay, so let's say there's all right, so how do we write symbols for that? Let's do the name first. So what name do I write? The name of the element.
Calcium.
Calcium dash what? Remember, this is going to be the mass.
42.
42. Protons plus neutrons is the mass. Protons plus neutrons is the mass. Now let's do it the other way. What's the element symbol?
Capital C, lowercase a.
Ca, and what's going to go down here?
20.
20, and what's the superscript?
22.
No?
Oh, 42.
42. 42. Okay, let's do it again. Let's pick a different color. Okay, so again, let's do just what we did here. What's the name of the element?
Okay. Zinc.
Zinc. And what number goes there? The mass.
58.
65.
65. Protons plus neutrons. Remember, we ignore the electrons. We ignore the electrons. All right, what's the element symbol? Does everybody understand that there? You got a question, you need to speak up. You need to speak up. Okay, so what's the element symbol here?
Capital Z, lowercase n.
All right. And what goes down here?
30.
30. Come on, why am I only hearing two voices? What goes up top?
65.
65. Okay, we'll do two more. And then I have a few things I want to say. Well, I wish they'd let me stay longer at the high school. I would like to do this Zoom class from the high school, but they kicked me out. All right, let's do, here's a good one. Oh, what am I doing? I'm supposed to be doing the other way. That's on the assignment anyway, I think. Let's see here. All right. So what's the name?
Argon.
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 And what goes there? What's the mass?
40.
Louder? Say
40.
40 is correct. 40. Okay, and let's do it the other way. What's the element symbol?
Capital A, lowercase r.
Okay, AR, and down here,
22, 18,
18. And up, and the superscript,
40.
40. All right, and one more. Any questions there? Any questions? All right, let's do one more here. Bum, bum, bum. Okay, what's the name? D block.
Gold.
Gold. Okay. And the mass?
199.
199.
Yeah.
All right, and the symbol is?
Capital A, lowercase u.
Gold, and down below?
79.
79 and
120.
120. Right, 79 and 120. Okay? So,
How
Something
come-
oh, wait,
It's
not
not
120.
190.
Yeah, it's not 120. What is it?
190.
199.
90.
199. Okay, so do we have any questions? You're gonna have to do this on the assignment, both ways. All right, both ways. It's simple enough. All right, since there's no questions, I just want to mention a few things here. Number one, how many total isotopes do you think there are in nature? Or sorry, not in nature, that scientists know. Roughly, how many total isotopes? Remember, there's 118 different elements. Take a breath mint here.
Somewhere up near 300.
300? Somebody else take a guess.
250.
250? Try 3,000. There's about 3,000. And they add new ones every year. Now, most of those are artificially created. All right? The average naturally occurring element, okay, we said there's 92 naturally occurring elements, even though there's really actually a little few more. But of the 92 naturally occurring elements, on average, there's about 29 known isotopes on average. All right? Hydrogen has the fewest, it has 8. Hydrogen has the fewest. So I do want you to know these numbers: 3,000 total isotopes and about 29 on average for each of the 92 naturally occurring elements. All right? Hydrogen has the fewest known isotopes, 8, but only 3 of those occur in nature. Only 3 isotopes of hydrogen occur in nature. Okay? And what are those 3 isotopes? Again, the
Deuterium, tritium.
Well, there's protium, which is 1H1 or hydrogen 1. It's just a proton, no neutrons. Just a proton, no neutrons. All right? Then there's whoever was saying that, there's deuterium, which is 1H2 or hydrogen 2. And then finally, we had, and somebody already said it, we have tritium. And you should be able to guess the mass there. Tri is 3. So the mass is 3. And written the other way, it's this. Hydrogen 3. I'm sorry, I kind of ran out of room there at the end.
We can't quite see that the board.
Oh, okay, thank you. Oh, yeah, because I turned my computer there when I was talking. Okay. So can you see it now?
Yes, thank you.
Okay. Yeah, sorry about that. So these 3 naturally occurring isotopes of hydrogen are the only isotopes up to 3,000 that have their own nicknames. They have their own nicknames. They're the only ones up to 3,000. And tritium was crucial during the Manhattan Project. Very crucial during the Manhattan Project. Look at your periodic table. Now remember, we said that those are average masses of the naturally occurring isotopes. So look at that mass on the periodic table for hydrogen. Which of these 3 isotopes do you think is the dominant isotope, population-wise?
Protium?
Which one? Protium.
Protium.
Is correct. Yes, because the value on the periodic table, what is it, 1.008? Yeah, 1.008, which is very close to 1. It's very close to 1. So that tells me there's almost none of these 2 in nature, right? Almost none of those 2. That's why during the Manhattan Project, they had to build a whole laboratory in Tennessee, Oak Ridge, just to produce tritium, right? I mean, if this were what they needed to make the first atomic bomb, they wouldn't have had to build a whole research laboratory to do that because it's the dominant form of hydrogen. Okay? What's the, excuse me, what do you think the dominant isotope is of oxygen? What mass?
16?
Say it.
16?
16. Okay, carbon is 12 is the dominant isotope, 14 for nitrogen. Okay, now if you look at chlorine, number 17, atomic number 17, you see its mass on the periodic table is 35.45. So there's actually 2 dominant isotopes for chlorine. One is 35 and the other is 37. But we see there's much, much more of 35 than there is of 37. If I remember correctly, the ratio for every 3 chlorine 35s, there's 1 chlorine 37. Okay, if I remember correctly. Okay, so now we know about the numbers of isotopes, and we're about out of time here. So right now, at the end of, I'm going to end the recording here.